Hi class. In this lecture here, we want to do a quick review of what indeterminate forms are, and we've talked about this in previous lectures when we were looking at limits. And then we're going to introduce a very simple rule called LHopitals Rule. Okay, so two things here. First, we're going to recognize limits that produce indeterminate forms. We'll do a quick review of what that is, and then I'll show you what LHopitals Rule is, and we'll talk about how you use this LHopitals Rule to evaluate a limit. Okay, so what exactly is indeterminate form? So, like, if you look here, indeterminate form is when you directly plug into a limit. Okay, what it's telling you, like this one here. Okay, so if we go to the limit as x goes to -1 of 2x squared minus 2 over x plus 1, and like you plug in this limit, so you get 2 times -1 squared minus 2 over -1 plus 1, and you see you end up just getting 0 over 0. And what we learned in previous lectures here was that, hey, when you get this indeterminate form, generally what you can do is you can do something to evaluate the limit here. And you know what we saw in this case here was there's something called the dividing out technique, and you know other forms of this indeterminate forms are things like 0 over 0 or infinity over infinity, as you see in this example here. And you could, you know, there was an algebraic method, or there was an algebraic technique as stated here, to solve. Well, I want to show you eventually another rule, or coming up in the next couple slides here, this LHopitals rule, which is an alternative way for evaluating these limits that have indeterminate forms. Okay, so let's talk about this LHopitals rule. And it just goes as the following. If f and g are functions that are differentiable on some open interval from a to b, and in that interval is c, now again, except possibly at c itself, okay, so it might not be differentiable at c. Assume that g prime of x is not equal to 0 for all x and b, except again, possibly at c itself. If the limit of f of x divided by g of x, okay, so as x approaches c, so this is the limit we're looking at here. Limit as x goes to c of f of x divided by g of x produces the indeterminate form 0 over 0. Then it turns out that this limit is equal to the limit as x goes to c of the derivative of the numerator, f prime of x, divided by the derivative of the denominator, g of x. Okay, and this provided the limit on the right or exists, okay? So this result can also be applied when the limit of this f of x divided by g of x as x approaches c produces any of the indeterminate forms, okay? You know, when you have infinity over infinity, or negative infinity divided by infinity, or infinity divided by negative infinity, or negative infinity divided by negative infinity, whenever you have these indeterminate forms, you can apply this LHopitals rule. All right. All right. So let me show you that this works on the next slide. Okay. So here is the rule again. Right. I'll write it on this slide. If you have the limit as x goes to c of f of x over g of x, and it produces that indeterminate form, then you get the same answer if you evaluate the limit of the derivatives of the numerator and denominator. All right, let's look at this one here. So if you have the limit as x goes to -2 of x squared minus 3x minus 10 divided by x plus 2. And look, if you plug in -2 here, you end up getting 0 over 0. All right, but one way we talked about how you would solve this algebraically was you're like, oh, hey, the numerator factors. And look, you can cancel out this x plus 2. And look, you can just plug this right in, and you get -2 minus 5. The limit is -7. Okay, but let me show you now using LHopitals rule. So I'm going to take the limit as x goes to -2 of this. And so what I'm going to do is I'm going to take the derivative of the numerator and denominator. So this becomes the limit as x goes to -2. This becomes 2x minus 3. And the derivative of the denominator here is 1. Well, look, now you can just plug this right in, okay? So you get 2 times -2 minus 3. You get the same thing. You get -7. Okay, so this rule works. All right, so all I want to do now is I just want to do a bunch of different examples of this so that you can see like some of the different cases that come up. And I want you to know that L'Hopital's rule, it won't always work, okay? It won't. And I'll talk about cases where it doesn't work, and then what you'll have to do for those cases. And it's a lot of fun. So it's kind of a little bit of a review going back and evaluating some limits. Okay, so let's do this one. Let's do the limit as x goes to 1 of x to the 13th minus 1 over x to the 5th minus 1. Well, look, if you plug in 1, okay, you get 0 over 0. So you get this indeterminate form, okay? So this becomes the limit as x goes to 1. Take the derivative of the numerator. This is 13x to the 12th. Divided by, take the derivative of the denominator. 5x to the 4th. Well, now you can just straight up plug 1 in. And look, you just get 13 over 5. That's it. Oh, let's try this one. Let's look at the limit as x goes to 1 of, let's do the natural log of x cubed all over x squared minus 1. All right, well, first off, use your rules of logs, right? Like, let me bring the 3 down. That'll make that easier. And now if you were to plug 1 into this, right, like the natural log of 1 is 0, and then you get 1 minus 1 is 0, so you end up getting 0 over 0. So just apply L'Hopital's rule. Take the limit as x goes to 1. All right, derivative of the natural log is 1 over x, so this is just 3 over x. All over the derivative of x squared minus 1 is 2x. So when you clean this up, you get the limit of just this, right? Keep, change, flip. The denominator then becomes 2x squared. And you can plug 1 right into this. And the answer is just 3/2. So that's great. That's great. All right, now let's try this one. Let's look at the limit as x goes to infinity. All right, so now we're looking at an infinite limit here of x cubed all over e to the x divided by 2. And so now here's the thing. If you were to think about this, so as x goes to infinity of x cubed, that goes to infinity. E to the x divided by 2 as x goes to infinity, that goes to infinity. So by just, intuition here, figuring this out, you get this infinity over infinity. So you get this indeterminate form. So let's see if we can apply L'Hopital's rule and see what happens. And it turns out we can. So the limit as x goes to infinity of x cubed over e to the x to the 1/2. So take the derivative of the numerator. So this becomes 1/2 e to the x divided by 2. I'm going to leave the 1/2 down there. It doesn't matter. And look, if you were to plug infinity into this, you get infinity over infinity. So guess what? That's indeterminate forms. So apply L'Hopital's rule again. And that's okay. You can apply L'Hopital's rule multiple times. this becomes the limit as x goes to infinity. Bring this down. This ends up being 6x, another 1/2, so you get 1/4 e to the x divided by 2. Again, you plug in infinity, you get infinity over infinity. So you apply L'Hopital's rule again. So this is the limit as x goes to infinity of 6, the derivative of that is just 6, over 1/8 e to the x divided by 2. And you can see as x goes to infinity, you get 6 divided by infinity, right? So by extension, this is just going towards 0. So what I want to do with this example here, and hopefully what you can see is you can apply L'Hopital's rule multiple times, and that's perfectly okay. All right. Let's do some examples now where maybe like L'Hopital's rule just doesn't work out, and how to handle those situations. Let's try this one. The limit as x goes to infinity of x divided by the square root of x squared plus 1. So again, if you plug infinity in the numerator, it goes to infinity. You plug infinity in the denominator, it goes to infinity. So maybe try to apply L'Hopital's rule here. Okay. Derivative of x is just 1. And you have to chain rule this, right? So think about this as to the 1/2 power. So it's 1/2 x squared plus 1. This becomes to the minus 1/2. And then the derivative of the inside is 2x. Well, the 1/2 and 2 cancels. Negative exponent comes up top. So I forgot the limit as x goes to infinity here. So this is the limit as x goes to infinity of the square root of x squared plus 1 over x, just by taking L'Hopital's rule. And you see we didn't get anywhere, right? Like it just flipped backwards, okay? So L'Hopital's rule doesn't work here, even though it was indeterminate form. If you were to apply the derivative again, you would just get the flip back here. So what you're gonna have to do is you're gonna have to apply another method, right? And you're gonna have to use the dividing out technique here, just to recall. So you're gonna divide both by x. Okay, square root of x squared is x here. So this ends up, I'm just going through this quick because we've done this one before. And look, this goes to 0, so you just get 1 over 1. So not every problem that you might see here, you can apply L'Hopital's rule to. So just be mindful of that. Even like, let's try this one. The limit as x goes to infinity of cosine of x over x. Well, you don't even get indeterminate form here, right? Like, as x goes to infinity of cosine of x, it just does not exist because cosine just oscillates between -1 and 1. So it's like, what is this equal to? How do I remember, right? And so just you have to use the squeeze theorem. And look, you can see here the limit as x goes to infinity of -1 over x. And you can obviously see here that both of those are going to be 0 here and here. So this is just 0. All right, let's do let's do a couple more examples here, and we'll end on just some problems where L'Hopital's rule will work, so you can get a little bit more practice with it. All right, let's try this one. Limit as x goes to infinity of x plus 1 all over x squared minus 8. Well, if you know, this goes to infinity, this goes to infinity, so that's, an indeterminate form. So apply L'Hopital's rule. Take the derivative of the numerator, which is 1. Derivative of the denominator is just 2x. And what does this go to, right? So as x goes to infinity, 1 divided by basically 2 times infinity. This goes to 0. Let's try this one. Let's look at the limit as x goes to infinity of x cubed over x plus 2. Well, apply L'Hopital's rule, right? Because this goes to infinity, this goes to infinity. So the derivative of this is 3x squared. Derivative of this is 1. And you can see that this just equals infinity. The limit does not exist. It increases without bound, but it goes towards infinity. All right, this will be our last one here. Let's look at the limit as x goes to infinity of e to the x divided by x to the 4th. Both of these go to infinity as x goes to infinity. So apply L'Hopital's rule. Derivative of the numerator, well, that's just e to the x. Derivative of the denominator is 4x cubed. Again, infinity over infinity. So L'Hopital's rule again. Infinity over infinity. L'Hopital's rule again. Well, again, infinity over infinity. So the last L'Hopital's rule, you end up with e to the x over 24, which you can see that just still increases without bound. So that also goes to infinity. All right, class. I hope it helps seeing these. And as always, if you have any questions, let me know.